Hello everyone. In this lecture, we are going to solve examples on our next shortcut method, that is when the right hand side function in the non-homogeneous differential equation is either trigonometric function or hyperbolic function. So let us see the examples. First example is solve the differential equation d square plus 3d plus 2 of y is equal to sine of 2x, which is non-homogeneous differential equation of order 2, and right hand side function is the trigonometric function. Let us see the solution. Auxiliary equation is d square plus 3d plus 2 equated to 0. That is the auxiliary equation whose roots are minus 1, minus 2, which are real and distinct roots. Therefore, complementary function is yc is equal to c1 e raised to minus x plus c2 e raised to minus 2x. Now we will go to find particular integral whose general formula is yp is equal to 1 upon phi of d of f of x. Here phi of d is d square plus 3d plus 2 and f of x is sine of 2x. As it is trigonometric function, so we know that in the trigonometric function, in the last lecture only we have seen this, how to obtain the yp. We are observing the terms d square terms in the phi of d, and we are replacing them by minus times a square, where that a is the coefficient of x in the trigonometric function. In this example, a is 2. Hence, we are going to replace this d by minus into 2 square, which is equal to minus 4. So we are going to replace d square by minus 4. Therefore, expression it becomes, so yp it becomes 1 upon minus 4 plus 3d plus 2 of sine 2x. Simplified, this will becomes 1 upon 3d minus 2 sine of 2x. Again here trigonometric function is there, so we must have d square term in the denominator, for which we rationalize the denominator, that is we multiply numerator by 3d plus 2 and denominator by 3d plus 2. Simplifying it, we will be getting it as 3d plus 2 divided by 3d minus 2 into 3d plus 2, which is 9d square minus 4 of sine 2x. So see, in this way we got d square term in the denominator, and now again replace it by minus of 2 square, that is minus 4. So that will give us yp equal to 3d plus 2 divided by minus 36 minus 4 of sine 2x. Now we will simplify this expression further, and we operate this operator 3d plus 2 on sine of 2x. That will give us yp is equal to 1 upon minus 40, 3 into derivative of sine 2x, which is 2 cos of 2x. So 3 into 2, that is 6 cos of 2x plus 2 sine 2x as it is. So 2 sine 2x, which is the required particular integral for the given non-homogeneous differential equation. Therefore, the general solution is, which is given by the formula y is equal to complementary function plus particular integral. So replace this yc and yp by their corresponding expressions, and hence general solution will be y is equal to c1 e raised to minus x plus c2 e raised to minus 2x minus 1 upon 40, 6 times cos of 2x plus 2 times sine of 2x, which is the required general solution. I hope you have got this example. For more clarity, see the next example. Solve the differential equation d square plus 1 of y is equal to cos x plus sine hyperbolic 3x. Let us see the solution. Auxiliary equation is d square plus 1 equal to 0. Roots are d equal to plus minus I. So which is purely imaginary numbers with real part as 0. So alpha is 0 and beta is 1. Hence, the complementary function is yc is equal to e raised to 0x is 1. So 1 into c1 cos x plus c2 sin x. That is the complementary function. Now we will try to obtain particular integral. General formula is yp equal to 1 upon phi of d of f of x. Here phi of d is d square plus 1 and f of x is cos x plus sin h of 3x. As there are two functions, we will operate these operators separately on each of these two. Therefore, it will becomes now like this. First function is the trigonometric function. Second function is the hyperbolic function. We know that if function is trigonometric, then we are replacing d square in phi of d by minus of a square. That means here we are going to replace it by minus 1, and in the second term it is hyperbolic function. So we are going to replace d square by a square, that is here it is by 3 square, that is 9, like this. Therefore, it will gives us yp is equal to 1 upon 0 cos x, because minus 1 plus 1 will be 0. So 1 upon 0 cos x plus 1 upon 9 plus 1, that is 10 sin h of 3x. So what we observed in the first term, denominator it is 0 now. So this first term is the case of failure, and therefore we have to apply the formula for it, corresponding formula for it, which we have seen in the last lecture. What is that formula? So formula is the particular integral of cos of x plus b. If phi of minus of a square is 0, then in that case particular integral will be evaluated as x divided by phi dash of minus a square cos of x plus b. So we will use this formula, for which to evaluate this phi dash of minus of a square, we need to divide phi of d with respect to d. So for the first term, the derivative will be what? The phi of d is d square plus 1, hence its derivative will be 2d. Therefore, yp it becomes now yp equal to x upon 2d of cos x plus second term as it is. Now this is very simple because 1 upon d is the antiderivative operator. So take the integration of this cos x function. So that will gives us yp equal to x by 2. We will operate this 1 upon d on cos x. If we operate it on x cos x, then also the final solution will be same. So x by 2 integration cos x dx plus 1 by 10 sin h of 3x. Integrate this cos x function, therefore yp will be x by 2 sin x plus 1 upon 10 sin h of 3x. So which is the required particular integral. Therefore, the general solution is y is equal to yc plus yp. Replace these yc and yp by their corresponding expressions. Hence, the general solution is y equal to c1 cos x plus c2 sin x plus x upon 2 into sin x plus 1 upon 10 sin h of 3x, which is the required general solution. We will see one more example for more clarity. Solve the differential equation d cube minus 1 of y is equal to cos h of x plus 2. This is hyperbolic cosine function. Solution. Auxiliary equation is d cube minus 1 equal to 0. Roots are 1, 1 comma minus 1 upon 2 plus I root 3 upon 2, and third root is minus 1 by 2 minus I root 3 upon 2. So there are total 3 roots, out of which one is real and 2 are complex roots with alpha equal to minus 1 by 2 and beta equal to root 3 upon 2. Hence, complementary function is yc is equal to c1 e raised to x plus, now this is the term corresponding to complex roots, e raised to minus 1 by 2x into bracket c2 cos of root 3 upon 2x plus c3 sin root 3 upon 2 into x. We know this thing, how to obtain the complementary function. We have seen in the previous lectures, one of the previous lectures. So, which is the required complementary function? Now we will try to obtain particular integral. Its general formula is 1 upon phi of d of f of x. Phi of d is d cube minus 1 and f of x is cos hyperbolic of x plus 2. As this is hyperbolic function, we have to express phi of d in terms of d square. So this d cube can be expressed as 1 upon d into d square minus 1. And then in this denominator, replace d square by a square, because this is hyperbolic function. Our a is here 1. So replace d square by 1 square, that is 1. Hence, yp it becomes now yp is equal to 1 upon d minus 1 cos h of x plus 2. This is the hyperbolic function, and in denominator we left with d, but we want d square as per our procedure. Hence, again rationalize the denominator, means multiply numerator by d plus 1 and denominator by d plus 1. So it will becomes now d plus 1 divided by d minus 1 into d plus 1 is what? D square minus 1 cos h of x plus 2. Again, see, in this way we got d square term in the denominator. Now replace it by 1. So we got yp equal to d plus 1 upon 0 of cos h of x plus 2. So see, with this our denominator it becomes 0 now. So which is a case of failure. And therefore we will use the formula when we will get the very first time case of failure. Hence this yp is equal to d plus 1 will be as it is, and because of this d square minus 1 we got denominator 0, hence we differentiate it. So yp will be, this formula we are going to use, hence yp will be d plus 1 into x upon 2d cos hyperbolic of x plus 2. Now integrate this cos h function. So because 1 upon d is the antiderivative operator, so we are going to integrate it. So yp is equal to d plus 1 into x by 2 integration of cos h of x plus 2 with respect to x. So its integration is sin h of x plus 2. So yp is now d plus 1 of x by 2 into sin h of x plus 2. Now operate this operator d plus 1 on the function x into sin h of x plus 2. We have operated the operator on the function x into sin h of x plus 2. So we got the two terms. Now we have to evaluate this first term. Second term will be as it is. To evaluate the first term, we need to apply the product rule of derivative. So apply the product rule, that will give us the expression 1 by 2 into sin h of x plus 2 plus x into cos h of x plus 2 plus x into sin h of x plus 2. This second term will be as it is. This is the simple derivative. Now simplify this expression further. Combine the last two terms, that will give us x into 2 times we can take x common and we can write expressions for cos h and sin h function, and we simplify them. We will get 2 times e raised to x plus 2, 2 times e raised to x plus 2, and that 2 will get cancelled. So we left with x into e raised to x plus 2. So which is the required particular integral, and hence general solution is y equal to yc plus yp. Replace the expressions of yc and yp, that will give us required general solution. So in this way we can obtain or we can solve the non-homogeneous differential equation using shortcut method when the right hand side function is the trigonometric or the hyperbolic function. I hope you understood this. Thanks for watching this video.